Hello and welcome everyone. My name is Dane Menke. I am the Digital Marketing Manager here at Regenesis and Land Science. Before we get started with the webinar today, I have just a couple administrative items to cover. Since we're trying to keep this under an hour, today's presentation will be conducted with the audience audio settings on mute. This will minimize unwanted background noise from the large number of participants joining us today. If the webinar or audio quality degrades, please try refreshing your browser. If that does not fix the issue, please disconnect and repeat the original login steps to rejoin the webcast. If you have a question, we encourage you to ask it using the question feature located on the webinar panel. We'll collect your questions and do our best to answer them at the end of the presentation. If we do not address your question, we'll make an effort to follow up with you after the webinar. We are recording this webinar, and a link to the recording will be emailed to you once it is available. In order to continue to sponsor events that are of value and worthy of your time, we will be sending out a brief survey following the webinar to get your feedback. Today's webinar will focus on navigating design and installation challenges in vapor intrusion mitigation. With that, I'd like to introduce our presenters for today. We are pleased to have with us Matt Ambrush, Associate Principal at Langen. Matt Ambrush is a licensed professional engineer in New Jersey with experience in both the investigation and remediation of environmentally contaminated sites. Over the last decade, he has become heavily involved in the redevelopment of brownfields and landfills for the purposes of mixed-use developments. He has extensive experience and expertise in the testing, evaluation, design, and optimization of vapor intrusion mitigation systems, and supports projects through the design, implementation, and operation of vapor and landfill gas mitigation systems throughout the country. We're also pleased to have with us today Ryan Miller, Director of Land Science. Ryan Miller directs a nationwide team of vapor intrusion mitigation experts in providing technical support for the design and installation of TerraShield, NitroSeal, MonoShield, and RetroCoat vapor intrusion mitigation systems. He also educates the environmental community on the advancements in vapor intrusion barrier technology, implementation, and quality control. All right, that concludes our introduction. So now I will hand things over to Matt Ambrush to get us started.
Thank you so much for that nice introduction, and thank you, Ryan, and the entire Land Science team for having me today to discuss, as you mentioned, design and installation challenges in vapor intrusion mitigation. So we're going to kick things off today. First, I just want to ground everyone in the conversation, get back to the basics, and understand, what are our objectives when we talk about vapor intrusion mitigation, and also some of the considerations, site-specific, that we want to think about when we are designing and implementing such systems, and then jump into the design challenges, implementation challenges, and the associated solutions that we have found to be effective. We'll also take a moment at the end to run through a quick case study that highlights some of the items that we'll be discussing today. So vapor intrusion mitigation objectives, this may be very basic and it might seem straightforward, but I think it's going to ground the conversation today and put into context some of the items that we'll talk about. First and foremost, we're designing and installing these systems to protect indoor air and human health. It's very obvious. However, when we're designing and installing these systems, we also want to consider constructability, adaptation, and operability of these systems. We'll get into this in a little more in further slides. But just thinking about, the design is only as good as the installation. So we want to design something that's constructible, that could be constructed, that can be protected, and that can be effective after it's been installed. Also, we know that these buildings over time, the use may change, the tenant may change, the conditions on site might change. So we want to be able to design something that's going to be adaptable as conditions change over time. And then finally, operable. The project doesn't stop after we've designed and installed the system. We also have to be sure that we can operate these systems effectively and make sure that they can continue to be protective of indoor and human health throughout the life of the building. And these concepts, these objectives need to be considered throughout the entire process. So pre-design, design, the bid process, the installation process, and arguably I could have another box there, the operation of the system. So when we talk about mitigation systems, there's a lot of different mitigation strategies. We've listed them here. We could block vapors, we can vent vapors, we can pressurize a building to prevent the intrusion of vapors, we can flush the indoor air, and we can also purify the indoor air. There are a lot of different strategies. Some are more conventional than others, and some are more appropriate in certain conditions. Since we're going to be kind of focusing on new construction here in this presentation, we're going to look at the first two vapor intrusion barriers and passive subslab piping systems. Arguably the same concepts that we're using in a passive system could also be transferred to an active system. The other items, the other mitigation strategies that I have listed there certainly can be effective in certain situations, but I would say in most cases not the preferred, not as conventional, and more often implemented in a situation where the building is already existing and there are other constraints that would prevent another mitigation strategy. I also have a note here down at the bottom that there are additional components that need to be considered for the mitigation of methane or landfill gas. A lot of the same concepts apply. However, I'd be remiss if I didn't mention that there are a few additional things to be considered. So again, design considerations, I think this is something that we're all familiar with and something we probably do without even thinking about. But again, for the purposes of today's conversation, it would be good to just refresh everyone's memory. So when we look at design considerations, every design is going to be site specific. While they're going to have similar components, similar elements, the same objective, there are going to be slight deviations or differences between each system based on the particular site. So when we talk about site conditions, we're talking primarily about contaminants of concern, and not just the contaminants of concern, but also the magnitude of those particular contaminants. Simple way of saying is how contaminated is contaminated. So those are some things to consider. Certainly also depth to water. When we're talking about a mitigation system, we're trying to mitigate vapors that might accumulate beneath the building slab. If that subsurface underneath the building slab is saturated, it's not effective or even necessary to mitigate vapors. The vapors aren't present because that subsurface is saturated. So things to consider. Also building type and use, and also the size is also going to play a fairly significant role in the type of system and some of the elements that we include, as we'll talk about on future slides, even materials of construction, and we'll get into more on that. The site plan, what is the ultimate plan for the site? Are we going to be filling the site? Are we cutting the site? If we're cutting the site, are we addressing through excavation maybe some of the impacts that were present that were creating a vapor intrusion concern? If we're filling the site, what is that fill composed of? Do we have an understanding of how that may or may not enhance or minimize the potential for vapor intrusion or preferential pathways for that matter? And then structural, architectural, and then the MEP designs for these buildings. Again, we're focusing on new construction primarily in this presentation. Our design cannot be designed, no pun intended, in a vacuum. We need to understand how our system is going to be incorporated into the overall building envelope, considering structural, architectural, and MEP. And again, this is where site-specific things come into play. Each building's constructed a little bit differently, and as a result, our systems are going to be designed a little bit differently. So the first one I really want to dive into is materials of construction. So I've listed here typical elements of any passive subslab mitigation system and some of the considerations for the materials that might be implemented as part of that. So we've got our aggregate ventilation layer. This is that layer that sits below the building slab, typically above the prepared subgrade. It's a high permeable layer, and it's intended to act as more or less a bathtub for vapors, where these are where the contaminated vapors can migrate vertically, collect in this aggregate layer, and where we effectively mitigate those vapors, moving them outside the building envelope. So we want this to be a high permeability material that allows air to flow very freely, very low on fines. Typically, this material can be an ASTM number 5 or 57 stone. It's most common, I would say. However, I will mention that while that's the most common, we have found that in certain locales, this material is more available than in others. So something you want to consider if you know that where your site is located, this material may be less common or harder to procure, might want to consider during the design phase what alternative materials could be used and propose that up front as opposed to a back and forth RFI and submittal process. In terms of mitigation screen, so now we have our mitigation screen that's going to sit within that aggregate layer, is going to act as the conduit for vapors to move from beneath the subslab and vertically out of the building. These materials are typically slotted or perforated PVC or HDP pipe. However, there are other elements such as J-drain or flat vent materials like TerraVent offered by Land Science. Each has its merits. There are situations where each makes sense. Certainly in a low profile situation, a flat vent material might make sense, or in a situation where you might expect to experience some settlement of the subgrade, maybe in a landfill condition. A flat vent material where you don't have to be concerned about pipes breaking might be a good alternative in those situations. Vapor intrusion barrier, I think this is probably the material of construction talked most about in these systems. There are a number of different types, and again, really depends on the application and the contaminants of concern. You have sheet applied, you have spray applied, and even in some instances, waterproofing membranes. If portions of the building are expected to be saturated and the structural design calls for waterproofing, there may be instances where that waterproofing membrane can double as a vapor barrier, or we at least need to consider how that waterproofing membrane is going to be tied into a vapor barrier in other portions of the building that don't require that waterproofing. Vent risers, again, that's the other element of this mitigation screen, a conduit of vapors out through the building. So mitigation screens are going to lay horizontally underneath the slab. These vent risers will connect to those and vertically transmit those vapors outside the building envelope. Not much to say here other than just be mindful of your local building code. I know, for example, New York City, interior piping needs to be constructed of a metal, whether that be cast or galvanized. A lot of other towns and cities, locales would not necessarily have that requirement, just something to be mindful of though, so that your systems are compliant with local building codes. Air inlets, something that we often include in passive systems to help promote the movement of air beneath the slab, since we are really relying on advective convective flow of vapors. We want to have every advantage to help move vapors from beneath the slab and out through the vent risers. And these air inlets we typically equip with a barrel ball valve, which would prevent the flow out of the subslab but into the subslab. So we don't want to certainly have these air inlets act as a conduit for vapors to come out and impact folks that might be at ground level. And then finally, the vapor monitoring points. These are intended to not only monitor system performance, but also to monitor vapor concentrations throughout the building footprint over time. And please, I make a note here, if we're monitoring for VOCs, let's please not use PVC glue, whether it's low VOC or not. That's going to be very difficult to distinguish between what's from PVC glue and what's actually in your subslab environment. So follow up to that, this is just a visual of what a typical mitigation system vertical profile looks like. So you've got your prepared subgrade. We often include a lightweight, maybe a 4-ounce geotextile placed over that subgrade, between the subgrade and our ventilation layer. Reason being is we just want to prevent the potential for any fines to make their way into that venting layer. Again, the intent is to have a very permeable layer for vapors. We don't want to have, due to construction activities, or in the case of active extraction in an active subslab system, have fines enter into that ventilation layer. We would then have our mitigation screen running horizontally within that aggregate profile. In this instance, we show a detail where we had a limited elevation to work with for our aggregate layer. So rather than our typical 6-inch ventilation layer, we worked with a 3-inch layer. So in that case, the flat vent, low profile screens made the most sense. Finally, on top of that, you've got your vapor barrier. And then in some instances, and we'll get into this in future slides, understanding construction sequence, means and methods, and understanding what's going to happen after the barrier has been in place. There are situations where adding a protection course on top of that vapor barrier to protect the barrier during construction may be applicable. And that's something that you'd want to coordinate with the overall team and also the manufacturer of that particular barrier to make sure everyone's comfortable with what's being proposed. And then finally, your building slab. Purpose of this is, again, just to drive home the point that every site's a little bit different, but some of these things really do have an impact on both the durability and the cost of the system. So it's not one size fits all, and being able to distinguish what elements need to be changed for certain site characteristics is very important to help maintain the durability and the cost of your system. Next is your system layout and just being mindful of building functionality and aesthetics. So when we install these systems, and this goes back to my comment earlier about considering the structural, architectural, and MEP designs for a particular building, we want to design something that is in keeping with the rest of the building and not hindering future functionality or in some cases aesthetics. So this layout I've got here, just to demonstrate the point, large warehouse facility. We typically in these instances try to co-locate our vent risers with interior columns. They can run up inside an I-beam, very nicely discrete, they're protected, and they're not encroaching on the floor of the warehouse and impacting future functionality. We don't want to impact functionality. We also don't want to have our system damaged. So it kind of plays a dual role in that case. Also, from an operability perspective, we want to be able to access certain components sort of at will and not have a concern, and in the case of a warehouse, of having a racking system placed over top of it or someone being hit by a forklift. So having some of these elements that we're going to be consistently looking at to monitor system performance, such as our air inlets or vapor monitoring points, having those exterior to the building is very helpful, again, from an operations perspective long term. And you can see here, these green dots here, those are our air inlets and vapor monitoring points that are accessible from the exterior. And then you've got this yellow dot here, which represents an interior vertical vent riser along a column. The next consideration, and one that gets talked a lot about, is vapor barrier durability. So I think the first point I want to drive home is thicker does not always mean more effective. There are a lot of things, a number of aspects that go into the effectiveness of a vapor barrier. Again, very site specific, but certainly thickness, durability is one of those elements. Materials of construction, and just compatibility with the particular contaminant. All of those things go into the effectiveness of a vapor barrier. But in terms of durability, what are some of the things that influence durability? Again, thickness, definitely. The thicker the material, I don't think anyone would argue it. Thicker would be more durable. Materials of construction, the way that certain vapor barriers are manufactured with different materials. So that's something to consider. And then the last one, which I think is maybe not always thought about, but is the anticipated activities following vapor barrier installation. So in instances where maybe you're installing a vapor barrier and there are no construction activities other than to pour the slab after the installation, maybe the durability is less of a concern. It's not completely eliminated from consideration, but it's less of a concern. There's a possibility that you might be able to do with a, let's say, thinner vapor barrier. However, if you know for a fact that there are going to be a number of construction activities, whether it be rebar and other things placed over top of the vapor barrier following installation, we would want to consider that. And those might be instances where you might consider a thicker vapor barrier. So certainly the materials themselves, thickness and the actual materials play a role. However, the intangible, the construction activities after the fact also play a role in durability. Some strategies to protect our vapor barrier. One, and most important, is communication. Just making sure the entire project team, from the GC, your concrete, flatworks contractor, and everyone in between is familiar with the system that's being put in place and understands the necessary precautions to be taken to protect the vapor barrier. Certainly, installing a qualified installer plays a big role. Having someone who's done this a number of times, knows what it takes, and can be an advocate on site for you as well, plays a big part. And then some of the other things that we talked about, protection layers, certainly talking with the manufacturer and the rest of the project team, understanding the vertical profile and any limitations that there might be there, but implementing a protection course so that there's a degree of separation between the barrier and those construction activities, limiting the construction activities, and then finally just observing the installation and monitoring after the installation until the slab is poured to make sure that things are being done properly to protect the vapor barrier. Specifically, constructibility considerations. Again, wanting to design something that is site specific, not putting our head in the sand and understanding that even if you've done a design for a warehouse, every warehouse isn't the same, or if you've done it for a residential structure, not every residential structure is the same. Understanding some of the different elements, being very familiar with the structural and architectural plans, and understanding how we might be able to preemptively plan for some of those elements. So an example of that would be tilt-up walls. I discussed earlier having these elements for vapor monitoring points and air inlets that are accessible from the exterior of the building. Understanding how we're going to actually get those elements out of the building and onto the exterior wall. So does that mean we coordinate with the fabricator and we put in preemptively sleeves for those particular elements? Or do we coordinate with the GC and say, things can change in the field, design the tilt up without the penetrations, and then we'll core on site to allow those elements to penetrate the exterior of the building? Just a conversation that should be had and be considered by all project team members. Similar things for pour backs, dock pits, elevator pits, those really come into play as, how are we going to protect the barrier? How's the sequencing of the vapor barrier going to happen? Some of these things don't happen immediately after one another. So if vapor barrier gets installed under one element of the system, it may be there for quite some time until it can be tied into the rest of the system. Allowing enough material to make that connection and protecting it and making sure everyone's on board, all very important. In terms of sequencing, when we're talking about construction, one big thing is, are they going to build the building first, or are they going to pour the slab first? Certainly, if the building is up before the slab goes down, that building is going to act as a great protector to our prepared aggregate layer, as well as any vapor barrier that might be installed prior to the slab being placed. Again, that's just a sequencing thing. If the slab is first and you've got tilt-up walls, then you got to be prepared for pour back areas. So again, just understanding the sequence and preparing the design elements and the design details accordingly for that, and getting the project team on board. Means and methods, another big topic that's always talked about, pumping or tailgating concrete. We'll get into that in a little more detail on the next slide. That's always a topic of conversation, and I think it's going to play a very large role typically in your vertical profile of your mitigation system, protection course or not, and thickness of your vapor barrier. That I think that plays a very large role in ultimately what your profile looks like. Concrete forms is another thing. We would love for Flatworks guys to not use stakes. Oftentimes that's not the case when they're putting their forms in place. So that's fine as long as everyone's aware that prior to the next slab being poured, next section of slab being poured, that vapor barrier needs to be inspected and repaired wherever those stakes were placed. Ideally, we can prevent that from occurring, but if not, having that proactive approach and getting folks on board. And then finally, the end use, understanding if a building is spec or built to suit. Concern with a spec building is tenant improvements in the future, and just understanding that measures are going to need to be taken to protect and also, in instances, repair the vapor barrier and other elements of the mitigation system if those tenant improvements are to occur. And to the extent we know where those tenant improvements may occur, maybe that vertical profile can change a little bit in those areas, whether it be the type of barrier, the thickness of that barrier, or even whether we include a protection course or not in those particular areas. The last thing I wanted to focus on, as I mentioned, is this concrete placement method. This is something that gets talked about a lot, is pumping or tailgating concrete. Certainly there's a premium associated with pumping concrete. It's everyone's preference to back the truck up and tailgate concrete, but there are concerns about running vehicles over installed sections of mitigation system or vapor barriers. So to the extent that maybe we can sequence or coordinate the installation of the system with pour sequence, maybe just stay one section ahead of the rest of the team so that we don't have large sections of mitigation system that need to be protected and that would allow for tailgating. That's certainly one approach that we've seen be effective, but that does require that coordination. I think the big takeaway is we never want to drive directly over top of the barrier. If it is determined that they want to move forward with tailgating and that sequencing is such that we can't just stay one pour ahead, we're going to have large swaths of system installed ahead of time. That's where that protection course really comes into play, having the conversation with the project team and saying, okay, well, there might be a premium for pumping concrete, but there's also a premium associated with installing a protection course over the entire footprint of the vapor barrier. So just having the wherewithal and having those conversations up front. And then finally, I think I had mentioned earlier, but having some of these conversations with the manufacturer as well as the installer. The manufacturer has a wealth of knowledge. They've seen a lot of these projects. They know what the materials and vapor barriers are capable of, and getting their input and buy-in is very important when installing these systems. So a case study just to kind of show the different elements that we've talked about thus far on the call today. This is a logistics center installed in the Northeast. It consisted of 7 approximately 500,000 square foot warehouse buildings. We did design sub-slab vapor mitigation systems with the monoshield system for all buildings on site. As I had demonstrated in a previous slide, we did include exterior access to much of the infrastructure. So our air inlets and our vapor monitoring points. We co-located our vent risers with interior columns. In this case, the building slab was poured before the structure. So we did have to consider, we do get some nasty weather here up occasionally in the Northeast. So how are we going to protect the barrier, sections of barrier that have been installed prior to the slab being poured? How are we going to protect the ventilation layer? The project team for this particular project, there was a combination of tailgating and pumping concrete. We did not include a protection course. So in situations where they could back the truck right up and we were able to limit the amount of mitigation system installed prior to the next pour, we did so. And then in some instances, combine that with pumping when necessary. And then finally, most of these buildings also experience tenant improvements. We did not, in this instance, include a protection course over the barrier preemptively for the purposes of tenant improvements. However, the entire project team was made aware of the situation and that any tenant improvements would need to be coordinated with the certified installer as well as us Langen as the design engineer. And that coordination went very smoothly. They knew upfront the expectations that were set. We had a few details, so there were no surprises when it came to the tenant improvements. As we conclude here, I wanted to just summarize a few big picture takeaways. One I've been trying to drive home during the presentation today is no site, and as a result, no system should ever be exactly the same. There's always going to be a slight variation, whether because of the architectural or structural design, whether it be site conditions, the contaminants of concern, the magnitude of those contaminants, whatever it may be, there's always going to be a reason that each system's going to be a little bit different and that we should be designing our systems accordingly. The other element of this is design is only as good as the installation. So again, no pun intended, we don't want to design our systems in a vacuum. We want to design these with the life of the project in mind and all the different trades that are involved. So making our system constructible and operable over the life of the project is very important because these systems need to operate not just on day one, but they need to operate throughout the life of the building. And then finally, just another element of this is just coordination with the entire project team throughout the process, not just during installation, but during the design process, during the bid process, and during the installation, and even after during tenant improvements, all very important. And I think if we consider these three takeaways in the future when we design systems, we'll all find that we'll have much more constructible and effective systems. And with that, this concludes my portion of the presentation. I'm going to hand it over to my good friend Ryan, who's going to take it from here. Take it away, Ryan.
Thanks, Matt. That was really good information. I'm going to take a few minutes and dive a bit deeper into the vapor barrier evaluation process, really from the manufacturer's perspective, and then discuss the importance of a good QA/QC system. So when looking at the evaluation of vapor barriers, we at Land Science talk about two main areas: chemical resistance, how well the vapor barrier blocks vapors, and then constructability, how easily is the vapor barrier installed. But I think there's a little bit more that goes into that. And so really, what factors should we consider when you see this list here? Chemical resistance is at the top, and really rightfully so. The need for a barrier to be chemically resistant is fairly obvious, but this is really the first criteria that design engineers, regulators will look at when they start their vapor barrier evaluation process. So, when you have a vapor barrier that's specified for a project, you should have testing that shows the barrier's ability to limit diffusion of those contaminants like chlorinated solvents, petroleum, methane, whatever it may be. And this is really quantified by measuring the flux of contaminant vapors across the barrier. And then from those results, developing a diffusion coefficient specific to the contaminants that were tested. And so next up on the list of factors to consider when looking at a vapor barrier is constructability. And we view this as kind of an umbrella word. There are a lot of things underneath that: durability, ease of installation, a certified installation. It's really all of these things that encompass the term constructability in our eyes. So when looking at constructability, you should be thinking about or evaluating the efficiency of the installation, how quickly, how easily can it be installed. Matt will be the first one to tell you the last thing you want to do is hold up a concrete pour schedule. Durability, again, which Matt did a great job discussing. Just remember, this is very likely an active construction site, and you want a vapor barrier that can withstand the level of that activity. And then finally, a certified installation, which I will discuss in the upcoming slides, but I wanted to touch on cost because that is really, the elephant in the room when it comes to vapor barrier selection. I'll say this about cost. There are a lot of things that factor into the cost of the vapor barrier. You have the material, sure, the cost of that, the cost to install the vapor barrier. You have additional QA/QC procedures. Are those being captured in the cost? Field coordination, oversight, potential repairs. Matt alluded to tenant improvements that may need to be handled after the fact. So I just bring this up because there's a bigger picture to consider when it comes to cost. So going back to my comment earlier regarding a certified installation, I do want to address the QA/QC program that really should be included in every vapor barrier installation. Just as a reminder, we often say a good QA/QC program is a safeguard to ensure that time, money, not wasted, or even worse, the entire system being rendered useless. Matt mentioned the design is only as good as the installation of the system. So, it's really important when looking at a QA/QC program, what is involved in that entire process. You have the pre-installation meeting, you have a certified applicator, third-party inspector, warranty, so there's a lot in there. And so looking at a pre-installation meeting, a pre-construction meeting, I'm sure you're all aware of these, you've attended these in the past, but in our eyes, it's a critical time to discuss who's handling what scope, who's responsible for what, what are the expected timeframes for certain aspects of the job, like QA/QC, smoke testing. Are there any contingencies in place for unforeseen issues, things like weather and the like? So it's just a really good time to get out in front of all of those things. Next, certified installer. Matt again touched on this, but they're highly recommended, if not required. And certified in our eyes means they've gone through training to learn about the system being installed. Kind of makes sense. You don't want someone that hasn't been trained or doesn't understand the system to be out there installing it. Certified installers know the obstacles, they know what they'll run into, and they'll know how to overcome those obstacles when in the field. So if your installer isn't certified for a system that they're planning to install, you might want to ask why, kind of dive into what training they've had. The goal, our goal, everyone's goal should be a vapor tight installation. So you just want to make sure the contractor that's doing the work is kind of capable of that. Third-party inspections. This is something that we recommend. Third-party inspectors are on site to observe, keep notes about the installation. They're taking pictures, recording site conditions, detailing core conditions, observing smoke testing. So it's not only good practice, it is actually required in some scenarios, especially if you're looking for an extended warranty on a vapor barrier. And then the last component of a QA/QC system is a warranty. So the system you have a warranty. Is someone going to stand behind the system for years to come in the future? It's just something to think about with respect to the vapor barrier that you're selecting. And so if you want to learn more about land science and the vapor barrier systems listed here, EverShield, NitroShield, MonoShield, feel free to reach out to me at any point, or feel free to reach out to anyone at Land Science. We'll take any questions you may have.
All right, thank you very much, Ryan. So that concludes the formal section of our presentation. So now at this point, we'd like to shift into the question and answer portion of the webcast. Before we do this, just a couple quick reminders. First, we will be sending out a brief survey after the webinar. We really appreciate your feedback, so please let us know how we did. Also, you'll receive an email with the recording as soon as it is available. All right, so let's circle back to the questions. First question here is for Matt. And Matt, the question is, how may different building uses impact the barrier system selected?
Yeah, sure. So as I had mentioned in that one slide, different types of barriers, primarily sheet applied or spray applied. We'll use two building uses as an example. Warehouse structure, for instance, very large square footage, quite often very few penetrations through that slab profile, maybe just in office spaces and maybe a utility or electrical room. Otherwise, very few penetrations. So in that instance, it may make the most sense from a installation and cost perspective to implement a sheet applied membrane. such as maybe a monoshield. Now, the nice thing about a monoshield too is that it's got the sprayed seams, sort of the best of both worlds there. You get the production and cost effectiveness. If we were to look at maybe a residential structure though, for instance, smaller square footages and a number of penetrations quite often, right, with different utility spaces, bathrooms, kitchens, and the like. So sometimes it is more difficult and less cost effective to use a sheet applied as opposed to maybe a spray applied, where it's much quicker to address some of those penetrations and smaller square footages.
All right, thanks, Matt. So here's another question here. This one's for Ryan. Ryan, the question is, what role does a geotextile fabric play in the vapor barrier selection process?
Yeah, so it's an interesting question because we've been seeing a lot more of this lately. The geotextile fabric placed either, I guess, underneath or on top of the vapor barrier certainly provides additional protection during the installation. So, if you think back to the case study that Matt presented, or me referencing an active construction site, the additional protection for the barrier system is really important. There are a lot of systems out there that don't have an additional protection fabric included, so they can easily become damaged during the installation. So incorporating a geotextile fabric certainly can be advantageous. There's no doubt about it.
Okay, thanks, Ryan. So here's another question. Ryan, the question is, can you elaborate on speed of the vapor barrier installation? What can we expect as far as timing goes?
Yeah, so, Matt certainly touched on this in his first question there, but a lot's going to depend on building type, warehouse versus multifamily. Again, the vapor barrier that's selected will certainly play a big role in the time it takes to install. So are you looking at a single sheet membrane that's installed, or a composite vapor barrier system like TerraShield? Those will have different times to install. The system you're looking at taped together, we found tape systems take significantly longer to apply than spraying the barrier. So there's a lot of things to consider when it comes to speed. Those are just a few.
Okay, thanks, Ryan. So here's another question for Matt. Matt, the question is, are there ways to prepare for future unknown tenant improvements in a spec building?
Yeah, a couple things to consider. I mean, one would be if you know that there are going to be significant tenant improvements occurring, you could consider, it's a bit of a more extreme approach, but you could consider installing a protection course over the vapor barrier prior to pouring the slab. And what that really does is, when someone comes to saw cut the slab and install utilities, they're not also saw cutting through your vapor barrier. So it adds that element of separation. That's one thing that you could consider. A deviation of that would be if you know primarily where the office spaces or where tenant improvements may occur, considering something similar to that in those particular areas. I think the more common approach would just be, and I mentioned it in the case study example, is just having that upfront conversation with parties that are involved and make sure that they're aware of the fact that this thing is not done after you've poured the slab. We're going to have to be involved after the fact if you start cutting into the slab, identifying what those details may look like so folks can prepare themselves for it. There are certainly instances where those tenant improvements happen after the fact, well after most of those parties have left the scene. So making sure that's incorporated into maybe a site management plan is another way to do so that those parties that are taking responsibility are aware of the fact that there's a system in place, it needs to be protected, and this is how you protect it.
All right, thanks very much, Matt. So that is going to be the end of our chat questions. If we did not get your question, someone will make an effort to follow up with you. For more information about environmental services from Langen, you can visit langen.com. If you would like to learn more about vapor intrusion barrier technologies from Land Science, please visit landsciencetech.com. Thanks again very much to Matt Ambrush and Ryan Miller, and thanks to everyone who could join us. Have a great day.